Hello everyone, once again I welcome you all to MSB lecture series on transfer chemistry. This is the 51st lecture in the series of 60. So, another 9 are going to be left after this one. So, let me try to complete the remaining topics and to give a completeness to this course, transfer chemistry course. Today let me start discussion on electron transfer processes. And so far we learned about the substitution reactions in square planar complexes, and then we moved on to substitution reactions in octahedral complexes, and we looked into two mechanisms or two pathways that usually follow. One is dissociative pathway or SN1 mechanism, and displacement or associative pathway, and that is SN2 mechanism, and also we showed how important both the pathways depending upon the type of complex we are dealing with and also the type of ligands we are working with when we perform a substitution reaction, and also I showed you how important the trans influence or trans effect in the substitution reactions of square planar complexes. And when we come to substitution reactions in octahedral complexes, again for first row transition elements, that is 3D elements, SN1 mechanism plays a major role because of the smaller size, whereas 4D and 5D metals have an option of showing both dissociative pathway and displacement or associative pathway. And of course, I also gave you examples to look into the stereochemical consequences in substitution reactions in octahedral complexes. Today let me start talking about electron transfer process. This is one of the very important process. This also we call it as redox process. What is redox process? Let us look into it. The simplest redox reactions involve only the transfer of electrons, and that can be easily monitored by using isotopic traces. For example, look into the example I have given here. We have taken two iron species, hexacyanoferrate 3 minus and 4 minus, and in both the cases iron are labeled, one is 56 iron and another one is 59 iron. When we perform or when we allow electron transfer by mixing these two, what we get is 56 FeCN6 4 minus, and then we get 59 FeCN6 3 minus. So, that means if you take MnO4 species and if you mix this one with unlabeled one here, despite the rapid precipitation of BaMnO4, incorporation of label has occurred already, and in this case precipitation is very rapid. According to Henry Taube, who got Nobel Prize in 1983 for his extensive work on reaction mechanisms, especially in electron transfer processes and redox processes, what he said is any substitution reaction should be complete within a 30 seconds. So, then you may ask why we continue for 6 hours, 7 hours, 8 hours. That depends on what kind of reagents we are using, what kind of substrates we are using, what kind of byproducts are formed. For example, if byproducts are always, if they are in solution, they can always tilt the equilibrium and go back to the back reaction. So, in that case what happens, for the completeness of the reaction and all drive the reaction from left to right completely to get maximum product or maximum yield, we prolong the reaction. So, let us continue talking about electron transfer processes. So, in the case of electron transfer between this tris bipyridine osmium 2 plus and 3 plus complexes, you know the fact that both are optically active, the rate of electron transfer can be measured studying the loss of activity. It appears very easy here. Once we mix these two and see what would happen, so optical activity changes. So, loss in optical activity can tell you or give a hint about the completeness of electron transfer process. For example, you take here this one plus here and we are taking minus here, and then plus becomes minus and minus becomes plus after redox process is over or after electron transfer is over. So, according to Henry Taube, electron transfer process can be classified into two types. One is outer sphere mechanism and other one is inner sphere mechanism. So, what is outer sphere mechanism and what is inner sphere mechanism? In an outer sphere mechanism, electron transfer occurs without a covalent linkage being formed between the reactants. So, that means we are bringing two species between which electron transfer has to take place. Simply you bring them together in the solution, it happens, electron transfer happens without actually bringing them with a bridging ligand. So, that means electron tunneling or electron hopping phenomena will come into picture. But in inner sphere mechanism, electron transfer occurs via a covalently bound bridging ligand. So, in this case whenever we want to explain using inner sphere mechanism or a redox process uses inner sphere mechanistic pathway, in that case what happens, electrons would transfer or electron transfer occurs through a bridge formation. So, that means we should invariably have a ligand that is capable of bridging the two metal centers, or it can exhibit bridging coordination mode. In some cases kinetic data distinguish between outer and inner mechanisms, but in many reactions rationalizing the data in terms of a mechanism is not straightforward. So, that means basically if we have a ligand in one of the substrates, preferably the one which is low spin, in that case what happens, the moment we identify yes there is a ligand that is capable of bridging, for example halides or hydroxide or any other bidentate ligands like pyrazine, yes you can tell probably when we perform redox process with this one, it would prefer a inner mechanism because there is a bridging ligand. But however, rationalizing just in terms of mechanism is not always straightforward. So, let us look into inner sphere mechanism. In 1953, Henry Taube showed inner sphere mechanism in the reaction of cobalt 3 plus and chromium 2 plus complexes, in which the reduced form were substantially labile, and the oxidized forms were substantially inert. Obviously, the reduced species would have more electrons and less oxidation state. As a result what happens, it becomes labile, it forms a high spin complex. On the other hand, that the one getting oxidized would be having smaller size, and then in that case what happens, even a weak field ligand can form low spin complex. So, his predictions looks very reasonable here. So, let us look into the reaction given here. We have taken pentamine chloro-cobalt 2 plus low spin a non-labile complex, because cobalt in +3 state the bond distances are very small and they have stronger bonds, low spin complex. And then we are taking high spin complex hexo-aqua chromium 2 plus. Now, once the redox process is over, the moment you see now substrate molecules, you should be able to tell which pathway this is going to follow when electron is transferred from one species to the other one. So, now this is the high spin now of the reaction, cobalt hexa-aqua cobalt compound forms a high spin, and then the chromium 3 plus, now chromium 2 plus has become chromium 3 plus, this is non-labile. So, that means all the chromium 3 produced was in the form of this one, you can see here. So, that means the bridging group has shifted from cobalt to chromium after redox process is over. And tracer experiments showed that all the chloro ligands in this one, in this compound is originated from this only. So, that means no other source of chloride was brought into the reaction, that chloride has originally from cobalt has migrated from cobalt to chromium ion. So, this is about inner sphere mechanism. You can see here, visualize the bridging intermediate or transit state here. So, of course, you know that chloride after establishing a covalent bond, it has still 3 pairs of electrons, and then a pair of electron can be readily donated to this one, and then one water can come out, and then it can establish a bridging like this prior to electron transfer. So, since cobalt 3 could not have lost chloride before reduction and chromium could not have gained chloride after oxidation, the transferred chloride must have been bonded to both metal centers during the reaction. This is what is very important. The intermediate species is consistent with these observations. So, then I have put different colors to emphasize about the nature of the bridging complex or transient species or encounter complex here. Chloride is transferred between metal centers, but such transfer is often observed. Of course, it is quite common to see this kind of inner sphere mechanism, as I mentioned, when we have a bridging coordination mode capable ligand on either of them. Let us look into another example here. Here I have taken the cyano complexes, the intermediate also I have shown here is stable enough to be precipitated as the barium 2 plus salt, similar to what we saw about BaMnO4. So, here also one can trap the intermediate by precipitating it out as a barium 2 plus salt. So, is slowly hydrolyzed to FeCN6 3 minus and then COCN5 aqua 2 minus without transfer of the bridging ligand. So, in this case what happens, the bridging ligand from the parent compound is retained on the same, it is not transferred, unlike the chloro situation in case of cobalt we saw in the previous case. So, that means now it is very clear, as long as we have a bridging ligand, yes, you can anticipate or speculate inner sphere mechanism for electron transfer processes. And what are the ligands that can promote this kind of reaction? They are all halides and OH minus, Cn minus. Cn minus also can act as a bridging ligand, and NCS and pyrazine. Of course, pyrazine is something like this. Something like this, and of course 4,4 dash bipyridine, not 2,2 dash bipyridine, it is 4,4 dash bipyridine. So, now we can look into the steps involved in inner sphere mechanism. 3 steps are involved in the electron transfer process involving inner sphere mechanism. First one is bridge formation, and then electron transfer, and then bridge cleavage. These 3 are the important steps involved in a inner sphere mechanism as far as electron transfer process is concerned. So, now let us look into the different techniques that we have at our disposal to study electron transfer processes to determine the rate of that particular process. Of course, now we have plenty of spectroscopic and analytical instruments at our disposal. No matter what the rate is and how fast or how slow a reaction happens, we can be able to determine the rate constant. If the reaction is very fast and the rate process occurs between 10 to the power of minus 14 to 10 to the power of minus 8 or 9, one can go for femtosecond and picosecond flash photolysis, or if it is in the range of 10 to the rise minus 9 to 10 to the power of 4, we have several options, nanosecond flash photolysis, or we can go for pulse radiolysis, or we can even go for NMR spectroscopy, provided we have NMR active nuclei in that species, and again it is not paramagnetic. Even of course paramagnetic should not be a problem now. However, if we have diamagnetic species, looking into NMR signals would be rather easy because we get sharp chemical shifts signals. And also we can also go for EPR spectroscopy if we have unpaired electrons, and then if the range is between 10 to the power of 4 to 10, then we can go for conveniently stop flow, or it is very slow, we can go for spectrophotometry or even isotope separation. So, we have ample experimental techniques readily available for studying electron transfer process. Let us look into the steps involved in the inner sphere mechanism. As I mentioned, the bridge formation, electron transfer and bridge cleavage. So, based on that one, 3 reactions I have given here. First you can see here 2 species are coming into the picture, and thus a corresponding back reaction rate also I have mentioned on top and bottom of these arrows. And now the first step is formation of this bridge with the elimination of one of the water molecule present on chromium. Next step is electron transfer. When the electron transfer happens, it has already happened, you can see here cobalt 3 has become here cobalt 3 has become cobalt 2 here, and chromium 2 has become chromium 3. That means electron transfer has occurred here. So, here bridge formation is completed and here electron transfer and here bridge cleavage. Bridge cleavage is there. So, that means these are the very important steps we come across in a typical redox process going through inner sphere mechanism. So, most inner sphere processes follow second order kinetics overall, and the data interpretation is very simple. So, you should remember just 3 steps: bridge formation, electron transfer and bridge cleavage. In the reaction between iron hexacyanoferrate 3 minus and pentacyano-cobalt at 3 minus, the rate determining step is the breaking of the bridge and is common for the electron transfers to be rate determining steps. That means, the always rate determining step is breaking of the bridge. That is the rate determining step. It is obvious that step is very slow, where we have an opportunity to learn or study or measure the rate of that reaction. For bridge formation to be rate determining step, in case if the bridge formation is the deciding factor, it is a slow step or it has to be rate determining step, the substitution required to form the bridge must be slower than the electron transfer. In a substitution reaction, if the bridge formation is going to be the rate determining step, in that case the substitution required to form the bridge must be slower than electron transfer. This is not so in case of this system, what we saw in the first case, cobalt, chloride, chromium system. Substitution in this one, high spin, is very rapid and the RDS, that means rate determining step, is electron transfer here. However, if chromium hexa-aqua chromium 2 plus is replaced by vanadium hexa-aqua vanadium 2 plus. So, this is a D3 system, vanadium is 3D3 4S2 D3 system, then the rate constant of reduction is similar to that of water exchange. This is true for reaction between hexa-aqua vanadium 2 plus and pentamine bromo cobalt 2 plus or pentacyanoazide cobalt 3 minus, indicating that the bridging group has little effect on the rate and that the rate determining step is ligand substitution required for bridge formation, this which is very similar to water exchange reaction. For this reaction, if you see here, I have given X a general one. So, where X can be considered different anionic ligands. For this reaction, for this particular redox reaction with a range of ligands X, the rate determining step is again electron transfer and the rate of reaction depend on X. The increase in rate along the series, if you go along the as halogen series increases or down the group, correlates with increased ability of the halides to act as bridge. So, the tendency to act as bridging increases as we go from top to the bottom in the halogen series. For both hydroxyl group and bromide, K is similar, but for water K is very small, is also pH dependent. So, this is consistent with water not being the bridging species at all, but rather hydroxyl group. It is available in solution varying pH. That means, this one, especially when we have this hydroxyl group, it is pH sensitive. Here I have listed data, you can see whatever I said. You can see here the rate is increasing, and in case of azide and OH is little, because here this is a pH dependent, whereas in this case water is not a bidentate ligand, or water cannot bridge two metal centers. And also through MO diagram, while discussing about bonding concepts, I showed you why water, despite having two lone pairs on oxygen, it does not act as a bridging ligand and it can at most acts as a terminal ligand, is because the second lone pair is little deeply buried and you cannot really activate to make water as a bridging ligand unless one OH bond is broken, then it becomes hydroxy group. So, as a result, what happens, you can see the influence of non bridging nature of water resulted in low rate constant here. So, that means now we have understood that as the ability to bridge for a ligand increases, the rate of redox process also increases. So, now with this let us look into outer sphere mechanism. When both reactants in a redox reaction are kinetically inert, that means both are say low spin complexes, electron transfer must take place by a tunneling or outer sphere mechanism. So, that means here we do not have any ligand to establish link between two metal centers. Of course, they are in solution, but what happens, electron should go from one to other one. So, reducing species getting oxidized and oxidizing species is get reduced, between them without establishing a covalent linkage, electron should be transferred. If that happens, what would happen? We call it as outer sphere pathway or outer sphere mechanism for such electron process reactions. Now, if we look into this reaction here, look very similar except for labeling on iron, isotopic labeling. This is 56 iron, and of course, oxygen states are different, hexacyanoferrate 3 minus with 56 and 59 hexacyanoferrate is 4 minus. Now, what we are getting for this one, delta G equals 0. So, but activation energy is needed to overcome electrostatic repulsion between ions of like charge to stretch or shorten bonds so that they are equivalent in the transition state. So, that means if we take one labile complex and one inert complex, it is not very easy to perform substitution reaction because of difference in the bond lengths of metal to ligand. So, that means in that context activation energy is very essential. For what activation energy is needed? It is needed to overcome electrostatic repulsion between ions of like charge to stretch or shorten bonds so that they are equivalent in the transition state. For example, if I take something like this, so they are not stable, so they keep coming, and also of course they are magnetic, you know that they try to interact. So, something like this, if I assume the bond distances are metal to ligand bond lengths are very different, in that case what happens? Before electron transfer process happens, what happens? Both of them should have a optimum or very moderate metal to ligand bond distance, so that they look alike in the transient state, so that electron can hop from one to other one. For this process activation energy is needed. That means we need to stretch the bond where it is short in case of low spin complex, in case of high spin complex we have to shorten the bond. This is also requires the alteration of solvent pair around each complex, because when this happens, what happens in the second coordination sphere, solvent molecules also have to readjust their position. So, that means in order to do this work also we need activation energy. In a self exchange reaction, the left and right hand sides of the equation are identical. So, only electron transfer and no net chemical reaction takes place. So, that means when we look into this reaction, it appears that there is no chemical reaction. Of course, there is no chemical reaction. Whatever the species we had, we also have on right hand side, but what happens? This loses electron and this gains electron and vice versa. So, that means there is no net chemical reaction happens. So, let us now look into the rate constant given for some outer sphere redox reactions at 298 Kelvin in aqueous solution. I have given here, look into this carefully and look into the rate also. We can get lot of information from this data given here. For example, if you just look into these two iron compounds here, and of course, you can see both of them are optically active, and one way, as I mentioned, the loss of optical activity can tell you about the process, and also to what extent it had happened also can give you, and how quickly that happened also can give you the rate. There is a way to measure. So, nevertheless the rate is in this order, and when we consider osmium more or less in the same order, they look almost alike. When we go for this one phenolphthalein, this is the value here. So, there is a drastic change in the rate. And then when we look into hexa aqua iron compound 2 plus and 3 plus, you can see here the rate drops, and then when you look into again ethylene complex here and 2 plus and 3 plus, again here 10 to the power of minus 4, and then when you go for this one it is even slow 10 to the power minus 6, and once again when we go for two different type of species. So, one we have bipyridine, other one is cyano, one is cationic complex, one is anionic complex, you can see the rate here. And then when you go for again phenanthroline in one case and a cationic species, other one is anionic species, rate is this much, and when you go for one iridium and one iron, rate is this much is here. So, that means now let us try to understand the rate process in this one and try to get some important information to conclude about outer sphere mechanism and how ligands play a major role in these reactions. So, let me continue little bit more discussion about this rate data I have provided here in my next lecture. Until then, have an excellent time reading, and I thank you very much for your kind attention.